And sorry. So his research basically focuses on stellar evolution and the feedback that stellar evolution has on the galactic scales as well. A few words about our speaker. So Manos graduated from the University of Thessaloniki, and then he moved to the University of Amsterdam, where he did his master's degrees, and he also graduated from there. His supervisor was Selma Demir, who is like she's an expert in stellar evolution and now currently a director at the Max Planck Institute for Astrophysics in Germany. So Manos had like an excellent supervisor and he learned from the best. Then he moved he moved to Geneva for a postdoc with Tassos Pagos, who is also an expert in stellar evolution. And then he moved back to Greece, working as a postdoc, as we said, at the National Observatory of Athens. And some more recent news about his career is that Manos actually was awarded one of the postdoctoral research awards from LIVEC. And he will be starting his LIVEC, or he will start his LIVEC grant at the University of Crete. So he will talk about deaths of massive stars in binary systems, and we are very eager to learn more about this topic. So thank you very much for this.
Thank you very much for the invitation. I'm very glad that I'm here. I hope that you can hear me. If I lower my voice or something, it's okay for someone to say that I should speak up a bit, because most of you are, I think, online. So I will not go again on the introduction. I'm Manos Zapartas, and today I'm right now at the National Observatory of Athens, and today I want to talk to you about corporal supernova from massive stars, and specifically from massive stars that are in binary systems. Okay, so to start step by step, why should someone care about corporal supernova? They are pretty much the cosmic engines of the universe because they provide the mechanical, and they're one of the main sources provide the mechanical and energetic feedback to their environment. They pollute their environment with heavy elements. That's one of the reasons that we are saying we are made out of stardust. They are the end fate of massive stars, so they give us constraints about the stellar evolution of massive stars. And when they die, they leave as a remnant a neutron star, a black hole, which is very interesting in its own. It can be also during a long gamma ray burst, if someone cares about these kind of sources. And in case that this compact object is found in a binary system, after that, maybe it can give rise to other exotic events like gravitational wave, the gravitational wave source, as an X-ray binary or a short gamma ray. And it can also be a source of cosmic rays and neutrinos. So historically, supernova term came because it has the term nova inside, which means new, because the idea was that it appeared as a new source in the sky, and because there was already another phenomenon which was nova, they had to put something that is more energetic and something about more energetic and luminous, so they put the super there. And it's already interesting to think that we see this new source usually in another galaxy, and it's difficult to pinpoint what exploded there, and that would be one of the key points that will come back again and again in this talk. From an observational perspective, as astronomy is driven by observation, we know that we see that supernova have a rise of a few days, and then it has a much more slow decay, and depending on its shape, we can classify them to different classes. And another sort of classification that we care about here would be from their spectral perspective. In case they show hydrogen in their spectra, we call them type 2 supernova. This is the most common supernova type. I will not talk about type 1a, which is a different mechanism of explosion. So I will not go much here. This is a wide of exploding, but it's still a very interesting, especially for cosmology. We'll go there. But now going again to the core collapse, type 2 is when they show hydrogen, and if they don't show hydrogen but they show helium, it's called a type 1b supernova, or a type 1c if they lack both hydrogen and helium. And in general, this field has been revolutionized, again, from an observational perspective, from the fact that in the last decade, there has been automated transit surveys, so surveys that look patches of the sky and wait whether there is a new information, something changing compared to before. And there they can quickly check and find that, oh, something's happening there, let's quickly check. And this way we can discover many new supernova per day right now. Now, I will be going, as I said again and again, that we see the explosion and we want, in many cases, to identify the bomb. Because it may be far away and we don't really see the bomb. We have a general idea of what kind of star exploding what, but as you can see, the debate is ongoing right now. So, starting from a stellar evolution that we know already from textbooks, we know that core collapse supernova are coming from massive stars above around 8 solar masses. And the reason for this is because these stars burn to heavier elements up to iron in their core, and we know iron cannot be fused anymore than produce energy. So when the fuel will stop, self-gravity will win eventually, and we will have the collapse of the core. That's why it's called the core collapse supernova. And we're going to have accretion towards the core. We're going to produce a proton-neutron star, it's called, in the center. And this accreted material will bounce and will create a shock now outwards that will drive away and unbind all the outer envelope and layers. And that's the explosion that we see. That's the general idea that we have. And in this context, the different classes that we see depend on what is the state of the outer layers at the moment of the collapse. If we see hydrogen in the spectra, it means that there is a hydrogen layer at the moment of the collapse of this star. If we only see helium, there is a helium layer, else we get more and more stripped, and that's where we think we get this sequence of more stripping. From a stellar evolution point of view, we know that massive stars in the Hertzsprung-Russell diagram, they spend most of their time during their main sequence, but when they evolve, they go to the red, they become cold, they expand a lot, they become red supergiants, and we expect these to be the main progenitors of type 2 supernova. And indeed, we have found also a lot of them. I will talk about type 2 supernova in the later part of my talk, but first I want to discuss about this class. So again, from the stellar evolution point of view, up to 1 decade now, we thought that more massive stars are very luminous, and we know that they have much stronger winds. And because of their own winds, they may eject their hydrogen-rich envelope and become observationally what's called Wolf-Rayet stars. And when this, if this explodes, when they're going to explode, they're going to give rise to a type 1b or maybe a type 1c. Now, in the last decade, there has been a lot of tension of this paradigm of single very massive stars being the progenitor of type 1b or being the only progenitors of this supernova. One of the reasons is that we have not detected a Wolf-Rayet star and confirming that it exploded in a type 1 supernova. The other reason is that in general, the ejecta masses that we infer from this type of explosions are quite low, of a few solar mass or maybe up to 5 solar masses, and we know that Wolf-Rayet stars are more massive. So where does this extra mass go? Does it go to the remnant in all cases? But if it's a neutral star, it's not easy. And another one is that observation, we find a quite high relative rate of this type 1 supernova. They are not as common as type 2, but they are quite high. And we know from the initial mass function that for higher mass stars, we expect pure stars. And if we really integrate and check how many we would expect, all Wolf-Rayet stars seem to be quite pure to account for all type 1 supernova. So there are some issues, some tensions there. In this context, lately, we wanted to bring one more issue, one more physical issue to this discussion. So first, I want to introduce here, we involved some stellar models with MESA. MESA is a 1D stellar evolution code. It's an open source code for stellar evolution for various kind of projects. And what I show here is the initial mass as a function of the final mass as a function of the initial mass. So we see, for example, that for a 10 solar mass star, in the end of its life, because of its own weight, it's only going to have around 9 solar mass, and it will be a 3 solar mass helium-4 and a 2 point something solar mass carbon-oxygen 4. And this part is the hydrogen-rich envelope, and we expect that this is the reason that if the star explodes, it will be a type 2 supernova. And we see that as we increase in mass, this hydrogen-rich envelope decreases. And at some point, there is a transition where we expect to have only a thin hydrogen-rich envelope. And if we have explosion here, it's going to give rise to a transitional type, which is called type 2b, that shows hydrogen for a few days. And after some other days, it stops showing hydrogen. And then for more massive ones, these will be the stars that we expect them to be Wolf-Rayet stars. No hydrogen there at the moment of explosion. If they explode, they give rise to type 1 supernova. I keep saying if they explode, and the reason for this is that there has been theoretical evidence and even some observational candidates that not all massive stars are able to explode in a supernova. The one that is shown from a numerical simulation that try to really catch the collapse, take into account magnetohydrodynamics, and take into account GR effects and neutrino transport. What they are finding is that when we have this shock that has to unbound the whole outer layer for the explosion, there are many cases where this shock stops, and we need to revive it somehow. The neutrino paradigm, which is the main paradigm that exists in astronomy right now for the explosion, is that a fraction of the neutrinos, if they are absorbed, they may revive this shock and have a successful explosion. But even in this case, right now, we are finding that because of the high accretion and because of the energy loss from the shock, in some cases, we're going to have a collapse on a black hole with no transient or a weak transient. So the stellar evolution textbook that we have that all masses touch are both solar masses, this is challenged right now. And here we see one simulation where we have an explosion with a neutral star formed there, and the other where we don't have an explosion with a black hole. Of course, so just to mention, there are even candidates, observational candidates of in surveys where they look at red supergiants and they wait, and they have seen red supergiants disappear. Now, did they become big? Did they really collapse? This is still in debate, but there are more and more evidence that supports this right now. Now, this kind of simulation are very, very computationally expensive, and they only simulate the very end and just for a few masses. So what we need when we go to populations is to somehow parameterize and to try to understand already from the stellar structure whether, like we want to predict whether a star will be able to explode or not. And there has been works that happened up now. What we see here is for some different physics and calibration, we have for different masses, some explosions here, no explosions here in a black hole. You see that it's really dependent on many of the physics, but we see some trend of explosion in this part of the parameter space and some non-explosion in this part of the parameter space. So what we did is we took these supernova predictive prescriptions and we applied them to our models that I discussed before. Our models reach up to carbon core depletion. This is a few years or tens of years before the actual collapse. It's very difficult to go further, and it's not easy to predict the collapse anyway. So we need this kind of mapping for the prediction. It turns out that whether it's going to explode or not depends a lot on the structure of the inner core and whether it's compact or not. And that's how we try to say, oh, this one is going to explode, the other not. And what I'm showing here is that for different kinds of prescriptions, where you see a line, we predict that there's going to be a successful explosion. When we don't see a line, there is no successful explosion. And for most of our prescription, apart from that one, which takes in a more sophisticated way turbulence there, but at least for the others, we see that most progenitors of type 2 supernova are expected to explode, but most massive stars that are expected to give us type 1 supernova are not expected to explode. I'm not saying that this is the final thing. This is dependent both on the stellar evolution assumption, on the mixing, on the overshooting inside, and on wind mass loss, and on the prescription. But it gives, if this was correct, it gives an extra issue of Wolf-Rayet stars being the progenitors of corporal supernova if they don't explode. And we played the game changing one assumption, which is the mass loss rate. We artificially increase the mass loss rate by 50%. And what we see is that, first of all, the transition to strip stars is happening at lower masses because winds are stronger and they can strip the hydrogen rich envelope before. And we have more explosions that are going in the regime of Wolf-Rayet and type 1 supernova. Still, many of them that are not exploding. So this would make the progenitors that successfully explode even fewer, and it's an issue at the rate again. Now, if Wolf-Rayet stars are not the main progenitors of type 1 supernova, then what explodes and makes a type 1 supernova? Now, it has been suggested already decades ago, pretty much, and it has been studied in the last decade a lot, the possibility that the progenitors are in binary. And what we have there, and that's my binary here. So the idea is that now we don't have just one star, but we have a companion in an orbit next to it. So when this star is gonna expand, trying to become a supergiant, we're gonna have the gravity of its companion winning on the surface of the star. And we're gonna start having an exchange of mass between the two stars. One star is gonna lose, one star is gonna gain. And binarity and mass transfer binarity I hope that people, can someone say that I'm still sharing and everything's okay? I hope that everything's still okay. Mass transfer in binaries provide a natural alternative for stripping a star. Even if it doesn't have strong enough winds, it will get stripped because of mass transfer of a companion. And we're gonna end up with a strict helium core because it lost hydrogen rich envelope. This core will keep evolving, will go up to iron production, and when it's gonna explode, we'll make a type 1 supernova. And what I just explained, this is not, don't think about it as an exotic phenomenon. that happens in some cases. For most massive stars, we would expect that this would be the normality, because we find most massive stars to be in closed binaries when they are born, so they will have some kind of interaction with their companion during their evolution, and that's what we're trying to take into account. And if we put this in an HR diagram, what we see is normally a star would go during its main sequence and will try to become a red supergiant that explodes here as a type 2 supernova, but because it has a companion, it's gonna get stripped. It becomes a helium star. It's going to go to the blue because it's compact and very hot, and it's going to explode here as a type 1 supernova. That's what we would expect. So we expect that the part of the parameter space that now expands, opens to lower masses that didn't have strong wings because of the luminosity, but can still be stripped because of binarity. Now, as I said, this has been studied. And again, speak about what this is studied a lot. I also contributed on the discussions. What I want to show here is something more specific where we don't focus so much on the star that explodes. We focus on the companion star. The companion star is the culprit that stripped the star that explodes and make it explode as a type 1 supernova. And the reason we want to focus on that one is because in collaboration with observers, we have, and there have been many people that have searched for this companion after the explosion. So in this case, for example, we have a type 1 explosion at 2013. And then when this supernova fades completely after many years, we go with HSP because we need a very good spatial resolution. And we try to find still a source there. And if there is still a source there, a stellar source there, we believe it's the companion that stripped the progenitor. And this specific one became also a press release of HST. And then the question comes and goes, okay, what should we expect to see there? We saw a star. What kind of star do we expect to see there? So we need to see it also from the theoretical perspective, and the main tool that we've used for this is a binary population synthesis code. This is a code where it enables us to evolve single star and mainly binaries of different masses of different periods as a population. So we don't only evolve a few, but we evolve millions of them in order to get the statistical properties of supernova and their companions in this case. One of the caveats of this kind of code is because we want to evolve millions of them, we have to simplify some of the assumptions that are going in and the inner structure of the star. So I would call them rapid population synthesis because they are mostly based on fitting formula or pre-computed single star models. So there is a limitation from this perspective there. In this, I've used one that is called binary C that work on these papers. And what we have found is that in 2 out of 3 cases of type 1 supernova, we would expect a binary companion to be there, and specifically an unevolved, quite unevolved binary during its phase sequence. So in most of the cases, we'd expect a star there. And we will try to get the distribution of what the masses we would expect. And that's what I'm trying to show here. So this is the cumulative distribution of the companion mass in type 1 supernova. These are the observations that we have because we are now on a phase where we can start, we have a small sample, but enough to start thinking about statistics. So this is the cumulative distribution of the masses of the companions, and with the dashed line here and with the dotted line here and with the shadings, I'm showing what is expected from population synthesis results with the rapid population synthesis code, which is called binary, as I just mentioned before. And the black ones are predictions that are coming from POSYDON. POSYDON, I showed this also in the first. It's I want to make now parenthesis to discuss about this. So Poseidon is someone could say a next generation population system because it's based on detailed binary models from MESA. It's a collaboration that is the main PIs are Tasso Frag at the University of Geneva, where I was in my postdoc before, and Viti Calogera at Northwestern. And the main idea is that we have computed extended grid of binary systems with MESA. So, for example, here, this is the parameter spacing M1 and period of one system, and just a slice in mass ratio between the two stars. Each point here, each square here is a binary simulation. So this is a very computationally heavy and difficult also because we need to check which one converge, which one do not converge, and how it would work. And that's the reason that up to now it had the version of one of Poseidon was out only for solar metallicity, and it's not incorrect. This is a mistake, sorry. And this is out. And this year we want to publish version 2 of Poseidon, which will have also lower metallicity, so that we will do population synthesis for lower metallicities too. And it aspires to be a community tool. It's an open source, as MESA is also. So if people want to use it, I'm also one of the developers, so I can help on that. Now, I want to do a small parenthesis that Maria already mentioned it in the beginning of my talk here. So I recently learned that one grant that I have applied as a PI in LIDEC got accepted, and from September, this project is expected to start at the Institute of Astrophysics in Crete. The main idea is to use Poseidon, so the code that I mentioned up to now, to study the feedback to the surrounding environment of single and binary stars during their life. So when they are still stars, during their death, when they explode, relevant to what we have been discussing up to now, and in case they remain as binaries during their X-ray binary phase. The main reason that I wanted to mention is that this grant will have an opening for a second person, for a junior postdoc mainly, but depending on availability, it can also be a PhD. So I wanted to mention it here if people are interested, or if people know people that may be interesting, mostly people that are finishing their PhD and are interested in stellar evolution, binary evolution, and the effect to the galaxy and to their environment. Please come in contact with them, or yeah, I have my email here, but you can find me in the National Observatory of Athens. So I close the parentheses. I'm going back to science here, and what we see here is that observationally we see a steep cumulative distribution of the companion masses. It's not so easy to really predict why do we find most of them to be at around 10 solar masses. We try to go back to each one of these observations and reanalyze whether we have this value correctly. But what we can already have as an idea is that the shading is for different assumptions in single and binary evolution. And we can already say that some assumptions like extreme conservative mass accretion of the companion seems to not be consistent with observation. So we can put a constraint in binary evolution knowing the companion at the moment of explosion. And we try to do the same thing when we put this observation in an laser diagram, and we see here the predictions from Poseidon of what stars we expect to be there at the moment of explosion. Most of them are on the main sequence. The observation seems to be on the higher side of what we expect. We see a few observations that are off the main sequence, and that's a question, why do we catch them at that point? Although there may be a caveat there, if a companion is there at the moment of explosion and the supernova ejecta hit that companion, the companion may be brought out of thermal equilibrium, something that we cannot model really in stellar evolution, that assumes hydrostatic equilibrium. And if it's brought out of thermal equilibrium, it expands and cools down. It looks like a giant without being a giant. Still, we expect this in a matter of few years to go back to equilibrium, and that's something we want to check. Okay, so I'll check the time.
You have 20 more.
Okay, great. Okay, so up to now I talked about type 1 supernova mostly. Now we change to type 2 supernova. So the ones that show hydrogen. In this context, pretty much, it doesn't seem that we need binarity to get progenitors of type 2 supernova, because we know that single stars are able by themselves to expand and become rich progenitors and explode the type 2 supernova. Still, we know that most of these massive stars are in binaries when they're born. So how would this affect the properties and the statistics of what we expect for type 2 progenitors? So again, from a theoretical population series perspective, we try to identify what are the main evolutionary scenarios to end up to a type 2 supernova progenitor. And what we get is that the most common one is this mass gainer. So this star that didn't lose the envelope as before, but gained mass as before. This is connected with the companion that I was saying before. If this star, after the explosion of the primary, if this binary gets disrupted, it would be free to become a red supergiant in an isolated state and explode as a type 2 supernova. But it had prior mass accretion before. Another main channel would be the merging of the two stars. What I didn't really focus much before is that when we have mass transfer between the two stars, we may have this mass transfer become unstable. And we're going to have one star kind of engulfing the other star and potentially merging in one new merger product, which will keep evolving as an isolated star. But it will have some differences compared to a normal single star, because mixing, it's an uncertain process, but we expect mixing to happen there. We expect a different structure to happen there, especially if it happens later in if the merger happens later in the evolution. And to tell the truth, probably the most well-studied supernova, which is 87H, well-studied because it happened at the Large Magellanic Cloud, very close by, still studied right now. Immediately, it gives us some questions because the progenitor we saw there was a blue supergiant progenitor, and it's not expected to think the stellar evolution to have a blue supergiant progenitor unless we tweak to some extreme assumptions, I would say, in mixing, etc. And a merger has been proposed as a potential scenario to explain this. So from a population synthesis perspective, we quantify how many times do we expect this to happen. And what we're finding is that indeed, in most of the cases when we see a type 2 supernova, it's probably a single star. This can be a very wide binary. We don't care about this when I'm talking about binaries. I'm talking binaries about that exchange mass. If they are very, very wide, they effectively evolve as singles. But in a not significant case, which can be up to half or 1/3, there are uncertainties in for sure. So don't take this value. Take this value with a grain of salt, I would say. But in general, it seems that there is no way not to have these two paths pollute our single star parallel in a way, and pollute in a significant way per rate. And it has been suggested that this can give rise to some of the observational characteristics that we see to some type 2 supernova. It can be one of the reasons of the diversity of type 2 supernova, These are some theoretical models of how different a light curve could be, and there has been some cases where the plateau was different, and they were trying to understand whether some binary mass transfer could explain it. But I want to go to something more specific today. So we see a type 2 supernova. We can even say that, okay, it's from a red supergiant, which it's not easy to say, was it a red supergiant that merged before? Was it a mass accretor? So we proposed lately a way to get an evidence whether this progenitor has a binary history or not. And this is by combining different observational methods in nearby supernova. So we talk about supernova that happen in galaxies of few or tens of megaparsecs away, where we can see the environment, we can see probably the progenitor. So I want to quickly discuss these methods here. One of the methods of trying to understand which star exploded is the direct imaging, where an explosion happens, and then we would check in our archive, did we observe this region before the explosion? And we go there and we see which star exploded. Okay, that's the most direct way of saying, okay, that's our project. And from its luminosity, we can infer its mass, given some uncertainty. Another way is if we get a spectrum late in the evolution of the supernova, hundreds of days after tens of hundreds of days after the explosion, from forbidden oxygen lines, we can get an estimate of how much oxygen we had in the core, how massive was the oxygen core, so how massive the star was before exploding, and given some stellar evolution factor consumption, how massive was initially. An independent way is to go to the region where the explosion happened and look at the stars around it. Looking at the star around it, we get an age estimate of the star formation that happened, of the population itself. And this would be the age of our progenitor. This would expect to be the most probable age of our progenitor, and this will give us a mass, because we know that more massive stars live shorter. So I can already show that when we go to a binary, showing an example, when we go to a binary example, these different observational techniques will give rise to a bit different results. And we can see here, let's assume an example, a common example of a 50 and a 6 solar mass star, let's say. At some point, the revolution, they emerge, and we are left with something like a 20 solar mass star, which evolves as a single star from now on, and explodes as a red supergiant, which would look luminous enough as coming from a 20 solar mass. So, with the techniques that I mentioned in the beginning, they will look at the luminosity and how massive the core is, and say, oh, that was a 20 solar mass star exploded. But from the perspective of the age of the population around it, this would not be a 20 solar mass age, because the main process that dictates what would be the time after explosion would be the slower evolutionary time scale of a 50 solar mass. Because until it expands, it will advance in a slower rate. So we would see this explosion, although it's from a luminous progenitor, etc., to be happening in a bit older population. And we think that this discrepancy can give an evidence for a potential binary history before. There may be cases where we have a binary history and this will not happen. But if this happens and we don't have another way to explain it, we're trying to understand whether we can pinpoint. I will mention this, it's a small parenthesis, but I think it's very interesting. In extreme cases, we can even go to very old ages, because binarity can help us violate the 8 solar mass threshold that I was saying, which is the threshold for a corporal. Because we will start just a little bit lower, and we have a merging of two stars, let's say a 6 and a 5 solar mass, during their main sequence, the merger product is expected to be able to do a proton, and is expected to explode even 70, 100, or even more mega years after explosion, because these stars evolve slowly. Now we try to put this in a quantified way, and we see the inferred initial mass from this method of age dating the region, and this method of looking at the pre-supernova phase of the progenitor. And for single stars, we would really expect one-to-one relation. One finds 10 solar mass, the other also finds 10 solar mass. But if we find that these that these methods are inferring higher masses, this may, turn on a light and say, oh, maybe it's a binary progenitor. And there has been observations with all of these methods to nearby supernova. There are big uncertainties in this. That's one of the main difficulties of trying to understand which one is there. Some of them are even upper limits, depending on whether in the surrounding regions also we have binaries, not for the progenitor, but even for binaries around. So we have this, and in a conference that I went 1 year ago, which was the first conference I went after COVID, it was, I sit down for a coffee with an observer, and we go, let's catch up how it's going. And I mentioned quickly this, and I'm like, okay, I think we can play with this, because there is one point here which seems that even given the uncertainties, at least where we had at that point, it's not in a one-to-one line. So let's check, could this be a binary progenitor there? And we went to have some extra analysis of these ones. This is supernova 2017 AW. And I'm showing again the idea here for that. It's kind of the same code with a different value parameter. Here we have the age, and here we have the final core mass. And for single stars, we expect progenitors with lower core to live longer, because they were coming from initially less massive stars. And for this specific supernova, we know that the core is in between these values, and we knew that the age is somewhere here, which is outside the single star regime. And this is what was expected from binarity. And we said, okay, this would be one of the cases where we have evidence for binary projection. Unfortunately, nature was not so kind to us, because when we did the reanalysis and we carefully tried to understand what was the age of the population around it, we pinpointed to be somewhere around here or here. There were kind of two cases of thousands. And one falls quite well, although in the threshold of the regime for single stars. So we cannot really say that this specific one was a binary progenitor. But we think that this can be applied to many of them that will happen, that have happened and will happen in the nearby. And if we have observation from all these methods, we can constrain and understand that although it looks like a single retroprojectile right now, maybe it was not before. How much time I have left?
5 minutes.
5 minutes, okay. I will quickly go on that one. One other thing that we tried to study was the red supergiant problem. The red supergiant problem, from a supernova perspective, is this one, where these are the observations of the masses, initial masses, let's say, or in reality it's luminosity, of stars that were found to explode in supernova. And we see that we start from around 8 solar masses where they expected, and go up to around 18 solar masses, given some uncertainties. Now, from the initial mass function, we would expect to have explosions from a few stars at least that are more massive, 20, 22, 25 for us. It will be fewer, but still we haven't seen any of them. Now, there is a big debate whether this is statistically significant, whether the discrepancy between the expected rate and not seeing a massive progenitor is significant. There are ideas that maybe these stars are the ones that implode in a black hole, and that's why we don't see them. That would be a nice way to solve it. We are not sure yet. But there was also the question, how would binarity change this? Because, sometimes we have an issue and there is an idea, okay, binarity is complicated enough that it can solve the issue. We found that in this case, binarity cannot solve the issue. We see that including mass gainers and mergers, as we said, are the main type 2 supernova scenarios, is not affecting the mass function of the progenitor, I would expect. And if anything, for this saving is for different binary physics, if anything, it can make it worse. Because, for example, if we merge a 15 with a 6 that I said before, we make it a 20 solar mass. If we don't see 20 solar mass stars explode, binarity made it worse because it created massive stars, which we don't see them explode. And then in the end, I want to go to the importance of the mass loss for progenitors of supernova, focusing mostly on type 2 supernova. Mass loss is important both for single stars and binary, right? All of them would care about. And there has been a lot of evidence that mass loss, especially in the very end stages of the star, as an evolver of the rest of them, but even years or decades before the explosion, should play an important role. In most of type 2 supernova, it has been found that there is circumstellar material around. This would mean a probable eruption before the explosion, some kind of episodic mass loss. And the question there would be, how would this affect the observation of this supernova? And just mention one or two more. There have been, for one specific type of supernova, which is called type 2N, which is with interaction with circumstellar material, there have been progenitor detections which are luminous blue violets, which at that point we didn't expect a luminous blue violet to be a progenitor of any supernova. We expect that it's a transitional phase in stellar evolution. But we found it that a luminous blue violet exploded. And we even have cases of type 1 supernova, so no hydrogen-rich envelope around it. After tens or hundreds of days, the supernova ejected to shift a circumstellar material of hydrogen. So an ejection of hydrogen happened just tens, hundreds, or thousands of years before the explosion. So these are all kind of reason, motivation to go to the study of mass loss in both single and binary. And this is where the assessed team in the National Observatory of Athens that I am right now is coming in. This is an ERC project led by being Alkis Bonanos. There was a talk of Alkis here a few months ago there. So I will not discuss much on that one, but pretty much the idea is we need to understand more the mass loss of evolved stars, and especially a low-metallistic environment. These are more far away, so up to now it was more difficult to study them, but we need to understand them in order to understand also the progenitors of corpuscular supernova. And specifically, one of the things I wanted to mention very briefly here is that there is a work in review already from the group which there are many works already published from the group, but there is one that has targeted and has the biggest red supergiant sample so far in the small Magellan cloud, and trying to understand the mass loss rate that we get as a function of luminosity. This is something needed as an input to our stellar evolution code. And it has been found to have a key and go to high values for high luminosities. And right now, I have applied some of these prescriptions in stellar evolution models, mega models within the POSYDON framework, trying to understand how this would change where we would expect red supergiant to be, and going further now, one step further, trying to understand where we would expect red supergiants to be at the moment of explosion, the final. And this kind of tripping would make stars lose most of their hydrogen-rich envelope and start going towards the blue. So it's one thing that I'm trying to work on right now. I think I will not go to more info that. I think I can wrap up and give a summary. I talked in the beginning about type 1 supernova, the ones that do not show hydrogen. From stellar evolution, we would expect that these would be good star progenitors, but binarity seems to be a more prominent scenario about it. Maybe a combination of these with the dominant binarity is what reality happening. I also discussed about the possibility of some of the massive stars not exploding, and that complicates this picture even more. And also in the binary perspective, where we want to start the progenitor, but we also start the companion next to it at the moment. So, and when we go to type 2 supernova, hydrogen-rich ones, we want to understand if we can identify a merger product or a mass gainer which has polluted our single star sample in a way. We think that there is a way if we combine some of the rational techniques. And also mass loss that I mentioned in the end, which is something that is important for all stars, and especially mass flow, uncertain mass loss in the above stages of the evolution close to the supernova that will alter how the supernova will look. Thank you very much.
So let's check if there are questions. Yes.
Yeah.
Let me check first the chat. Okay, so we can start asking questions now, and there are some questions by Despina here. So maybe you can. Yeah.
Thank you very much for a very, very nice talk. Very informative and very clear, so thank you for that. So I have a few questions. I have lots of questions, but I will restrain myself. So the first one is about this method about the counterpart star. The binary, what is left over, let's say, the second star that you can see after the explosion, after the supernova goes away completely. And you go back and look at the image and you say that is the progenitor.
The companion.
The companion. These are all quite far away. So the resolution, even for the HST, I'm not completely convinced, because I've seen proposals like that. I'm not completely convinced that you can actually pinpoint that that particular star that you see close to that position is not actually a projection and is really connected to the explosion. That's one thing. And the other is about the star formation history. That also has a lot of question marks there, and you can have lots of solutions for the star formation history. It's not always completely clear how well, you saw it yourselves when you did that, and you have two solutions for the same.
Yeah.
So these are helpful, but I don't think they can completely, maybe in a big enough statistical sample, they can help you, but not for probably for specific cases. And the other thing is, what about kick velocities? Have you, have you considered that?
Let me go to that. So I will hear.
Yeah, good.
So you're right. This complication there, whether we are really seeing the companion, is not an easy thing to change. And we are trying to solve it mostly with from two ways. One is if we have an SSD, at least to understand that it's a stellar software and it's not something else.
True. Yeah.
The other would be that from statistics, especially if we know that most of them we would expect them here, if we see something that is a main sequence regime, we're trying to understand that.
Okay.
We're trying to say that's what we say, that's what we get. That's kind of how it is. And especially if we have cases where it's not in a crowded region and it's as close as possible, and that's why we need HST, to try to say it's not in a dense region. It's still, we cannot say that.
It can be
Nothing.
projected because you never know the line of sight distance.
Like a foreground,
Yeah,
foreground
of course, or background.
or background. Or that. Yes. So we're trying in a statistical way of trying to say as possible.
Yeah.
Would this be
You-
a main sequence
Yeah.
star there, or would it be something else? And we're trying, but it's an estimate. And we're trying with statistics, like it could be something growth.
At least I think the negative is more certain. If you don't find something that is consistent,
Well,
then-
that's very true.
yeah.
So I didn't really mention, but a few of them are upper limits.
So it's not.
So we went there, we checked, and we know that there is nothing below this. So we know that if either there was nothing there or
Or
there
it's
was
less
some
massive.
upper. You're right. This is a clear constraint.
Yeah. That's a clearer, I think, more useful even.
Yeah.
And I wanted to say about this thing here, that this is very abrupt, which is not very consistent with the models, I think. How certain are we that there are no hidden systematics in the observations? Because that's a killer there as well, I think.
So we are pretty much, these are observations, like each one of these is a paper.
Yeah.
And right now, it's the first time we're trying to bring all of this together.
You can see all the hidden systematics.
We analyze it, see, so these people mentioned, 11 solar
You have
mass.
to
Is it really
reprocess
a
everything.
solar mass?
Okay, great.
And reprocess it, maybe go to the luminosity phase
Mhm.
and try to understand where this is. Which
Okay, great. Thank you. I don't want to monopolize the discussion, so I'll keep the rest of the questions for later. Thank you.
if there are
Let's see.
not many questions, there was another one for the methods that I can mention on.
Yeah, we'll keep on.
Yeah. Yes. So we have taken into account the velocity of the because this companion search can happen to supernova. It can even happen to supernova remnants, things that are here. The problem there is that we don't have a very good idea of what was the supernova, but these are close, and we have a better spatial resolution. There, the peak velocities are important because in a 5 or 10 years time between the supernova and checking, the kick is not low. But in a supernova remnant time, 1 kilo-year, it is. And we have studied what are the expected velocities of the companions if this system gets disrupted. Order of magnitude, they are expected to be as much as the orbital velocity at that point. The peak is around a few to 10 kilometers per second. With a tail being up to 30 kilometers per second and more. This tail would be identified as a runaway, as a star that goes different compared to its surrounding population. The ones that have a few kilometers per second is more difficult to identify whether they are or not, but still, that's okay. And in the supernova remnant case, we really need to backtrack the probability of, if we go back 1 kilo-year Is it where the supernova happened or not?
So
One,
you have a bubble where, an allowed bubble where you can find.
exactly. And still, just to have, these velocities are much lower than the supernova ejection. So in all cases, this stuff will be in the center of the supernova and or close to the center.
If you have also, like the online participants, if you have questions, you can raise your hand and you can ask Manos. Let's wait. Yes, or yes, unmute yourselves if you want.
I hope I was clear the audio. Thank you.
In the meantime, let me ask you a question. So I didn't really understand how you map this failed supernova explosion or the implosion, because it looked to me very irregular. So there was no pattern, and it was rather random the way that some of the stars exploded or not. So how did you map this and review it in meta calculation?
Yes. I can show maybe one example of that one. So stellar, so when we really do when the people do the numerical supernova explosion, they know if it explodes or not, given their physical assumption. In our case, we know that the structure of the inner core plays an important role whether the shock can unbind or not. And there have been studies where we try to parameterize a stellar evolution structure and say, will it explode or not? One of these parameters is called the compactness parameter. It's something like a term of mass over radius of a specific region. And the idea there was that when this is high, we are more prone to black hole explosion. It's not easy to say this will explode, this will not explode or not, but this will be more prone to not explode. Whereas if it's low, it's more prone for successful explosion and neutral substance. And as we can see, for this parameterization, this is not monotonic as a function of mass. And other people that have tried other parameterization, they still don't find it monotonic as a function of mass. The main reason for this is that there are some thresholds, for example, around here, where there are some abrupt changes, which is whether we're gonna have carbon burning of the shell in a radiative environment or in a convective environment. And this will change the structure of the star. And this will happen quite abruptly in a mass range. So this is beginning to give rise to this bar here, which kind of tells us that these masses maybe are not exploding. To tell the truth, when people are going to 3D simulations, even in research, they are finding that this is not consistent. That's why I try to use many supernova prescription. And to tell the truth, we need to go further. We don't have the answer still there.
So in the POSYDON calculations or simulations, what are you using exactly?
So in the POSYDON calculation, the main one that we have is we are trying to parameterize this from the CO, the carbon oxygen formats, and the carbon abundance. In this work, they try to find a connection between implosions, which is this, and explosion, which is this. So we have this in POSYDON. We have our stellar evolution codes going up to carbon for exhaustion. And with these two parameterization, we're trying to say this is probably going to explode, this is not. The general idea is the more massive the core is, the more difficult it is. Stars of 10 solar masses in all cases are found to explode, but 20, we don't. 50, we don't. There are people that are saying turbulence should go there, and that's definitely true. So this one. This is latest in time. Is supposed to be even more informed physically from having some terms for turbulence there. There are some other physical issues that we go there, and we see that the landscape changes a lot. So by far, I'm not saying that we know the answer there, but we know that this complication is there. We cannot just say everything is.
Go back to that image that showed the bank for the, and there was another peak at 40 solar masses. Okay, that may be an artifact of the fact that we are using a one big point, or two.
One stellar evolutions, all stellar evolution.
Yeah, it's all right. And we said that might be causing some systematic cells. Okay. But in any case, what causes this huge peak around 40 solar masses?
There's a true that very know which one specifically. I think I don't want to say something that's I don't remember if there was another physical reasoning for this.
Yeah.
Or they just said, given some
That's
given
just one
or
of the
some.
other I understand. And it's also quite broad and it's understandable, but this is quite sharp.
It's not maybe when I saw the landscape here. What I saw before is the one that showed that we had exposures here, then we had probably explosion, again explosions,
Yeah.
and maybe like this peak seems to be there. And that's the same group because it's not an indirect way. But you can see like even more massive on some of them.
So it's just a combination of complex parameters. And how does the surface of the proto-neutron star and the conditions there play a role? I mean, is that a parameter or is it the same always?
So in the ones that go through the simulation, they even like this is the proto-neutron star that is one.
Yeah.
So they read them.
Yeah, but
In
the
the
rigidness or whatever is always the same, or do they have a range, or is it always exactly the same? I don't know.
So I think they are playing with this, but I think it doesn't play such a big role on the simulation that really do the collapse. On the stellar simulation that are close to the collapse, then you don't even reach this regime. You just have a density profile trying to understand if a shock, like if you say, okay, let's assume a proto-neutron star, the center really goes in something, and we have a shock, will we combine the rest of it?
Yeah, I understand. But the shocks, cinematics, dynamics, if they are affected by.
But I think this is not the main video of surface. It would be mostly how many neutrinos are absorbed the moment that this shock stops.
If I may ask one more question or two. One is rotation of the core. Is this included in some of your calculations?
Yes, yeah. So in the ones that are shown with the rapid populations, you can see these are not all rapid populations do not have. In POSYDON we have. And so in each binary meta simulation that we have in POSYDON, we take into account differential rotation inside us. We take into account times between the two sides. And we also take into account the most extreme cases where we may have so high rotation that we have chemically homogeneous solution. This is an extreme mixing of bringing part of the envelope inside the core and then. And one of the main reasons that we are doing this, as considered as possible, is that we want to know the rotation of the core at the moment of the collapse. If it's highly rotating, it can give rise to long gamma reverse at the moment of collapse. And it can also, like, part of this angular momentum will go inside the remnant, and we see this in gravitational wave sources. When we get binary black holes merging, we know their chip mass, we know also their chi effective, which is a way of a combination of the spin of the two black holes. So we need to care about the spin, and we take into account in all our mesa grids. Now, during the evolution, when we go with black holes, there are some cases where we need to match it. So it's not one mesa simulation from beginning to black hole, but it's taken into account as self-consistently as possible. Same thing for you, like if someone cares about spinning neutrons.
Yes, thank you very much.
Thank you very much for providing me.
I wish there were more of us earlier, actually, physically, it would be better. Thank you.
Okay, thank you very much, Moni.
We keep in touch.